Welcome back, everyone. Today's lecture is about shrinkage. Shrinkage is essentially efforts to shrink some of the weights that you learn during a regression algorithm. And I'll go over why we want to do that. Our first algorithm for doing shrinkage is called ridge regression, which essentially takes least squares linear regression and adds a regularization term to the cost function, with the specific goal of keeping the weights from getting too big. It's also known as Tikhonov regularization. Under that name, it appears in a lot of other fields that are very different from machine learning. You often see Tikhonov regularization as a way of making engineering solutions more stable in inverse problems. So it's used a lot in engineering, for instance, in a way not so different from how we're using it. So in terms of the three-part menu of things you can throw into a regression algorithm that I gave you 3 lectures ago, what we are combining is the usual least squares loss function plus we're going to take the mean of all of the losses, but we're going to also add an additional penalty term. And putting those things together, we get the following optimization problem. I want to find a set of weights that minimize. We're going to start off with the standard least squares objective function, but then we're going to add an additional function to the end of that. So I want to minimize this thing. And for short, I'm going to call that J of W. J is our cost function. Find W that minimizes J. You might notice that I put a little prime on the W here. What does that mean? Well, I don't exactly want to take the 2 norm of the whole vector W. I want to leave out the bias term. So to do that, in the cost function, when I write the 2 norm squared of the weight vector, I'm not actually including the bias term, the last component. So a reminder that we are using the fictitious dimension here. We usually use it when we do regression problems so that our hypothesis doesn't have to be 0 at the origin. But although we want to penalize most of the weights, we usually don't want to penalize the bias term. I mean, you can if you want to, but it doesn't necessarily make sense to do so. So again, this thing looks just like least squares regression, except we've added this extra thing called a regularization or a penalty term. And the purpose of adding that regularization term is often called shrinkage. What is shrinkage? It's to encourage the weights to be small. And so the natural question you might ask is, why do that? Why do we want to make the weights smaller? There are a couple of reasons to do this. The probably original motivation for doing this is that it helps guarantee that you will have positive definite normal equations, not just positive semi-definite. So we no longer have to worry about the problem that comes up in least squares regression that we have an underdetermined system of equations, now we always have a unique solution. So the situation where we care about this is, recall that if you have a set of sample points in feature space that all lie in a common hyperplane, then the x transpose x matrix that comes up in the normal equations will generally be singular, and so you can't solve the linear system. So an example, a particularly common example, is when you have points that actually have more features than sample points, when d is greater than n, in other words, then you will always get singular normal equations in standard ordinary least squares regression. But in ridge regression, that's not going to happen. We're always going to get a positive definite matrix. And I'd like to kind of show you what that looks like in graphs. So here's an example where on the left-hand side is a graph of a least squares cost function. On the right-hand side is a ridge regression cost function for the same data. So in the example on the left, the main thing we notice about this is that this is not a quadratic form of a positive definite matrix. It's a quadratic form of a positive semi-definite, with the outcome in this case that all of these points here are minima of that function. You could pick any one of those points, and it's a perfectly good least squares fit. But the fact that we have to choose is not maybe ideal. Ridge regression essentially is equivalent to adding something to the diagonals of the system matrix that we're solving, so that now we just have one unique minimum. Now, when you have a problem with multiple solutions on the left, in engineering at least, and just numerical mathematics, you'll often hear that referred to as an ill-posed problem. Ill-posed, because it has more than one solution. Whereas on the right, we've transformed it into a well-posed problem by adding a small penalty term. And that is kind of what the term regularization originally means, is taking an ill-posed problem and turning it into a well-posed problem. So this was probably the earliest motivation for doing it this way, using regularization, doing ridge regression. But there's a second reason which has become more important in machine learning than this reason, which is that regularization also tends to reduce overfitting. Now, in terms of the bias variance trade-off, the way that regularization reduces overfitting is by decreasing variance, albeit at the expense of increasing the bias. Well, if you can decrease variance more than you increase bias, then it's a win. You get better generalization in that case. So a natural question you might ask again is why? Why does regularization help to reduce variance? It's a little tricky to explain that, but let's imagine a scenario where you have a bunch of points and you do a linear regression, and the output regression is, I think the correct regression coefficients are 500 times x1 minus 500 times x2. So suppose that's the best fit. But suppose that those numbers, 500, seem really suspiciously large. Like, why would we be suspicious of those numbers? Well, imagine that the points in feature space are well separated from each other. Like, they're not super close to each other. They're at distances of 1 or 2 from each other. But the labels are all in a narrow range. You know, they don't go below 0 or above 1, for instance. Then you would expect the coefficients in that case to be like single-digit numbers. You won't expect them to be 3-digit numbers. So in a situation like that, it's natural to be suspicious of these numbers. They probably represent some sort of numerical instability in the system of linear equations that we're solving. The issue here is that we see that small changes in x are causing big changes in y, because the coefficients are so large. But when we actually look at the scale of points that we're hitting to, it doesn't make sense that such a small x change should cause such a big y change. So when you see that happening, we suspect overfitting. We suspect that shrinkage will help get us a better solution. So a kind of kludgy way to achieve that is to penalize large weights. We just say the bigger a weight is, the less I trust it, the more likely it is I think that that weight comes out of the numerical instability of the problem and isn't actually a true representation of the data. All right, so this second reason to use regularization is actually closely related to the first one. Because remember, in the first motivation I told you about, we're taking an ill-posed problem and turning it into a well-posed problem. In the second motivation, what you'll see on the left-hand side is a problem that's almost ill-posed. It might not actually be ill-posed technically, but it's within a small perturbation from some ill-posed problem. And we want to make it sort of better posed, even though that's not a formally defined thing. We want to make it more stable, which is a formally defined thing. All right, so I want to come back to understanding this cost function. When we find a set of weights W that minimize that cost function, what does that mean? What does it look like? I think one of the books has a nice way to illustrate that, but I have redrawn it because I was a little unhappy with the drawing in the book, but this is just a different version of a drawing that you'll also find in Introduction to Statistical Learning, figure 6.7. What I've done here is I've drawn 2 different sets of isocontours, one for each of the 2 terms in the cost function. So remember, the cost function itself is this, the standard least squared cost function, plus lambda times this. So let's look at the isocontours of the first term and the isocontours of the second term separately. The isocontours of the first term are in red here. So that's them. The isocontours of the second term are in blue there. So the first ones are ellipses, and they're centered at the actual solution of the least squares linear equation with no regularization. So this point here, that is the standard least squares solution as we taught it 3 lectures ago. The isocontours of W squared are circles all centered at the origin. It's W squared, that's it. And the solutions that you're going to get when you find the W that minimizes the ridge regression problem are always going to be points where one of the red isocontours is tangent, just barely touches one of the blue isocontours. So right there, that's a solution to the ridge regression cost function for some value of lambda. And I've actually sketched solutions for 3 different values of lambda. Oh, by the way, I should say what the axes are here. The horizontal axis is the first weight, W1. The vertical axis is the second weight, W2. For simplicity, I have set the bias term to 0. So let's pretend for now, to keep these functions simple, that there's no fictitious dimension, that we're just fitting a regression that is 0 at the origin. And so we only have 2 weights, W1 and W2. This is what it might look like in that case. So coming back again to these solution points, again, I said those could all be solutions to the ridge regression problem just for 3 different values of lambda. Well, what about all the other values of lambda? Well, if you look at all the solutions to the ridge regression problem, they all actually lie on a curve that connects the solution to the least squares problem with no regularization. In other words, the point that is the least squares solution is also what you'll get for ridge regression if you set lambda equal to 0. Because lambda equals 0 just means no regularization term. At the other extreme, if you set lambda all the way to infinity, you wind up getting the origin. Because essentially you're penalizing the weights so infinitely that the weights have to be 0. Which is not a useful solution, obviously. But on that curve connecting the 2 extremes, you'll find potentially useful solutions. How do we choose which lambda gives us the best solution? Validation. The answer to everything is validation. You want the solution that's going to generalize the best on your validation data or your test data. So validation is how you choose lambda, which we treat as just another hyperparameter. Yeah, question?
Could you explain why the solution to the overall objective function is the point in which the 2 curves are tangent to one another?
Why is it that the solution is where the 2 curves are tangent to each other? Suppose I were to pick a point where the curves are not tangent to each other, and I tell you that is the minimum for some value of lambda of my cost function. Can you see why I'm lying? Yeah, exactly. So if I take my point and I slide it along the red line here, I can find a different isocontour blue isocontour that's inside the original blue isocontour. So if you do not have a tangency between those 2 curves, you can always walk along one of the curves and find a better solution with lower cost.
Okay, so you're saying that the blue is the size of W.
Yeah, the blue is the size of W, that's right.
I see. Okay, so you're saying for a solution, the size of W and the least square value that corresponds to the solution are on the line that we picked.
Are on the line, like the curve I drew over here?
Yeah.
Yeah.
Okay.
Yeah, I'm claiming that all solutions that are where 2 isocontours meet tangentially lie on this black curve that I drew.
Okay, got it. And then when you pick the lambda value, you're going to where the solution lies. The red line.
That's right. The lambda value is essentially a slider that takes us from lambda equals 0 at one extreme in this direction up to the origin at the other extreme. Mm-hmm. Question? Yes. When you add L2 regularization to this function, it's still going to be convex always. Yeah. Assuming it was, yeah, absolutely. In fact, this kind of makes it more convex because you go from having a positive semi-definite matrix in your system of equations to a strictly positive definite matrix. Yeah. If we don't penalize the bias term, is there any chance of the bias term? No. I mean, if you want a full mathematical proof, I would have to do that some other time you could ask on Ed, but in short, what the bias term does is if you have some sets of points that you're trying to classify or trying to fit a curve to, the bias term just moves up and down with the rest of the data. There's always going to be, so essentially, this is the f of w direction, and this is the w direction. No, sorry, that's feature space. If you imagine these are points in feature space, and I'm trying to fit a point to them, forget about the colors, they're all the same class. If I'm trying to fit a line to those points, then all the bias term does is it determines, is it this line, is it this line, is it this line, is it this line? Always there will only be one best solution there. Other questions? Mm-hmm. Oh, how do you find the solution? Well, that's what I'm going to talk about next. Let's solve this equation. Now that we know what we're doing intuitively. Hmm? If you have the lambda, you solve the ridge regression problem. Calculate. Yeah. That's right. You have to calculate the answer W by solving a system of linear equations and plot it on that. Mm-hmm. So let us see how to do that. What we're going to do is same thing we did with linear least squares regression, is you just take the cost function that I wrote down, you compute its gradient, you set that to 0, and that gives you a modified set of normal equations. I'm not going to go through the intermediate steps. I think you all know how to do this by now. But once you do it, this is what you get. Now here I'm introducing another notation. This I prime is analogous to W prime. It's basically an identity matrix, except not quite, because we're going to take the very bottom right entry of this identity matrix and set it to 0. Because we are not penalizing the bias term. And by the way, you might ask, if I set that bottom right entry of I prime to 0, is this matrix always really going to be positive definite? And the answer is, if we are using the fictitious dimension, and if we have therefore added a column of 1s to the end of our design matrix X, then yes, you can prove that this is always positive definite. It's never indefinite. Or, sorry, never semi-definite, or never just semi-definite. Never has a zero eigenvalue. So the ridge regression algorithm actually is pretty simple, or at least if you think solving a linear system of equations is simple, then this is simple, because the algorithm is just you take this equation here and you solve it for W. W is the only unknown in that equation. We know everything else. And once you've solved for W, then the regression function that you can use to estimate the hypothesis on future points is just W transpose times Z. So that's really the algorithm. It's that simple. So again, we are treating lambda as a hyperparameter, and the effect is that the bigger lambda is, the more regularization we're going to have, and therefore the smaller weight vector we're going to have. Now, if you recall from the previous lecture on the bias variance trade-off, we had a data model where we assume that each label is defined by some unknown ground truth v. We multiply x by v, and then we add a noise vector. This is our model of what happens when we try to gather data in the real world, is that noise gets added to our data. Well, you can actually compute what is the variance of ridge regression. And when I say variance, I mean as I described it last lecture when I talked about the bias variance trade-off. And if you work that out, what you get is that the variance of ridge regression is equal to the variance in the standard statistical sense of variance of this thing here. I know this looks a little bit complicated, but really the part you want to focus on is the fact that the matrix that we solve in our linear system of equations comes down here and then gets inverted. And so, remember, lambda is our parameter. As lambda gets bigger, that means that the variance gets smaller. Again, because we're inverting it here. So you can actually quantify how much ridge regression reduces the variance of the method as a function of lambda. And if you crank lambda up very, very, very big, then the variance actually goes to 0, which sounds great, except there's a problem that the bias goes up. So in one of your textbooks, Introduction to Statistical Learning, they have a little graph that shows you what this looks like for one particular ridge regression problem that they solve. And so in this chart, the horizontal axis is lambda. So we're seeing what happens as we crank up the ridge regression hyperparameter. The vertical axis is the amount of error and you might ask, training error or test error? Well, both. So no, not both, just the test error, sorry. Test error. And so we see this characteristic curve where when you go too far to the left, you're overfitting. When you go too far to the right, you're underfitting. And the way that we can explain this now is if we use synthetic data so we know what the variance and the bias is, we can actually plot them. So this green curve is the variance that I wrote a formula for up above. And the black curve is the bias squared, which is, you'll recall, the expected value of the hypothesis minus the ground truth squared. And in the limit as h goes to 0, in the limit as lambda goes to infinity, so as lambda is going all the way to the right, the variance goes to 0, as I already told you. But if you crank it up too much, then the solution itself is 0. So our hypothesis becomes 0 in the limit as lambda goes to infinity. And so obviously, if you go too far in that direction, you have a completely useless solution. So the bias is very large. And so the optimal point, the best choice for our hyperparameter, is somewhere in the middle where the variance is starting to go down, but the bias hasn't gone very far up yet. Any questions about that? Yeah. If we do what to the bias term? Oh. That's true. That's true. H doesn't necessarily. The bias term is still there, so you're right. If you're using the bias term and not penalizing it, then H won't actually go to 0. So take this as what happens if either you set the bias term to 0 or if you penalize the bias term. But the difference is kind of in the noise. You're still going to get really big bias when you make lambda too large regardless. Mm-hmm. Yeah. Yeah. You don't understand how we got this? Because I didn't cover it. Sorry. I don't. If you look at my lecture notes, I have like a bonus page at the very end. I did not have time to give that, and you're not responsible for it on the exams either. But there is a bonus page in there that explains how to compute the variance of least squares regression. If you are interested, you can go and find a derivation there for least squares regression, and then it's very easy to update that for ridge regression. Other questions? Yeah.
Why do you know the red curve is the test error, not the training error? Or what happens to the training error?
The training error tends to look a lot like the variance. So, or no, not the variance, the bias. So they didn't plot it, so I don't really know for sure, but I would say that this curve is not only the bias, but it's a very rough approximation of the training error as well. Other questions? All right, I've said it several times, but I'll write it down too. Lambda is a hyperparameter. And we tune it the way we tune most hyperparameters, by validation. Or cross-validation if appropriate, if you've got a small amount of data. So another thing I want to mention about ridge regression, which does not generally apply to standard least squares regression, is that you probably want the different features to be of the same sort of size, or in other words, it often pays to normalize each feature so that each feature has the same variance. Well, why do we need to do that? Well, remember that you might have different features that are completely different units of measurement. So if one feature is measured in miles and one is measured in seconds, they're not comparable to each other. But our penalty term kind of assumes that they are all comparable to each other. So when we write that and penalize that, we're penalizing the weight that goes in front of the length term, the same as we're penalizing the weight that goes in front of the time term. But those might not be comparable. By normalizing the data so each feature has the same variance, then they are comparable, and then it makes sense to penalize each of the weights in this vector equally. This is not the only way to do it. You might ask, well, why don't we just penalize the weights in that vector unequally? Well, we can do that too, instead of normalizing. But it's kind of equivalent to normalizing, where we say, let's use a sort of asymmetric penalty. Asymmetric in the sense that it penalizes some features more than others. And the way you can do that is you take I prime and you replace it with some other diagonal matrix where the diagonal items are not all the same. They don't all have to be ones. So really these two choices are kind of equivalent. You can show that if you choose the right entries on that diagonal, then both these methods will give you exactly the same solution. So there are two different ways to achieve the same thing. A situation where it might make a lot of sense, though, that's worth pointing out, is if you are doing polynomial regression. It does not necessarily make sense to expect that the weight associated with a degree 2 term would be the same order of magnitude as the weight associated with a degree 5 term. Depending on your data, different monomials of different degrees may need to be penalized differently. And so that's something you might want to keep in mind if you ever try to use, say, a quadratic regression function to interpolate your data. Any questions about that? So the next thing I want to do is kind of add one more section to the previous lecture. Remember, lecture 12 was all about how do we statistically justify using these cost functions. Well, ridge regression has a statistical justification too. And it comes through an application of Bayes' theorem, giving a method that some of you might have seen before called maximum a posteriori. I do not have time in this class to describe maximum a posteriori in any detail. And this is probably the only application of it that I'm going to give in lecture. So I will not linger on this. But here's the rough idea. Our model is going to be, I don't trust big weights. I trust little weights. If the weights are small, I think they're highly plausible. If the weights are 1,000,000, I think that's ridiculous and someone has screwed up. So I'm going to express that presumption about what kind of weights are likely to be plausible and what weights are likely to be implausible as a probability function. So I'm going to pretend, that the true weights that really govern the physical process I'm trying to understand come from some normal distribution with mean 0 and whatever variance. Then what I'm going to do is I'm going to apply maximum likelihood estimation. You'll remember last lecture, lecture 12, we used MLE to explain why, if you have normally distributed noise in your labels, it makes sense to do least squares regression. Now what I'm going to do is repeat that. We're again going to use maximum likelihood estimation to come to that conclusion, except there's an extra twist, which is now instead of just maximizing the likelihood, we're going to maximize a posterior probability that takes into account both the likelihood and this prior probability that expresses my prejudice about what weights are reasonable and what weights are unreasonable. So here is the use of Bayes' theorem to do that. The posterior probability that I care about is the likelihood that I will get a particular set of weights given a particular input, the sample points x and their labels y. And I can write that as, well, the likelihood of getting a particular set of labels given sample points and weights times, here's where we're going to use our prior probability, meaning this. So what I'm going to write down here is the PDF for that normal distribution. Divided by the likelihood of getting those particular labels from those particular points. So I've made a lot of underlying assumptions here that you need to untangle in writing this. The first thing is you'll see there are 4 different f's in this equation. They are not the same f. I just want to clarify that they're all PDFs, which is why I wrote f for all of them, but they're completely different PDFs. They're not the same function. So if it helps you to think about them, you can call this one f1, this one f2, this one f3, this one f4. Not the same function. But you should think of them all as being like a probability, only like a conditional probability, only for a non-discrete distribution, a continuous distribution. The second thing that is kind of hidden, but is a very important assumption if you want to get this expression, is I am treating w as if it is a random variable. I'm treating the labels y as if they are random variables. But I'm treating x as a constant, a fixed constant. For the purpose of this expression, x is not random. All right, so if you believe that this is a reasonable posterior to write, given those two assumptions I just told you about, then, well, this expression right here, that's essentially the likelihood that we derived last week for least squares regression. So I can just write as a shorthand, that is the likelihood that a particular weight vector will produce those labels. And then that is times our prior function here, which is, the PDF of that distribution, divided by this conditional distribution. I don't care about that denominator because it does not depend on W. We want to find the W that maximizes that posteriority, that posterior that I just wrote down. So what value of W maximizes this? Well, remember, when we maximize likelihood, we generally take the log so that we can turn the products into summations. And so that's going to be the log of the likelihood, the same likelihood that we did last week, plus the log of my new prior that I am introducing today, minus some constant. And if you remember in the previous lecture, what this essentially broke down to is minus some constant times the square of xw minus y. Minus a constant. And what about this one here? Well, that's just a very simple isotropic normal distribution with mean 0. So that is going to be minus a constant times the square of w prime. And then there are a bunch more constants that we just agglomerate together at the end there. So I really want to maximize that. And so maximizing that, well, of course, this constant doesn't matter for maximizing that expression. It's not going to affect which W maximizes it. The other two constants do matter, but what really matters is their ratio, because I can just take that objective function and divide through by the first constant. And when I do that, that is equivalent to the problem of minimizing xw minus y squared plus some other constant times w prime squared. So just to be clear, this lambda here, that's just an arbitrary constant that comes by taking this constant and dividing it by this constant. And so, as you can see, that is the ridge regression cost function. So by starting with this prejudice where I say, I think big weights are unlikely and small weights are likely, and then applying Bayes' theorem, and we wind up deriving this ridge regression cost function. So that's how statisticians justify why that's a good cost function. Questions? Any scenario where you would expect big weights? Big weights are usually the thing about big weights is that there's so many directions you can go big in, right? So there are many more big weights than there are small weights, because big just means further away from the origin or further away from the center. So in that sense, just on the bounds of the fact that there are much more of them, any one of them is much less likely to be right. So I am not familiar with any contexts in which big weights would somehow be favored over small weights. Yeah. Well, why are we leaving out the bias term here in the prior probability, but keeping it everywhere else? You do need the bias term. So you can't leave the bias term out of the least squares problem itself. What this is saying is just that I think that I do not trust big weights, but I am okay with trusting a big bias term because I don't actually know how much bigger or smaller the bias term should be than the other weights. If I had some information about that, like what is the relative scale of the bias term to the other weights, maybe I would throw in a penalty up there. But in general, I don't have that information, so it's easier just not to make assumptions about it. Yeah. Lambda is, where did lambda come from again is the question. Lambda is equal to a quotient of two constants, meaning this constant here divided by this constant here. We're just dividing the whole equation through by the leftmost constant. Other questions? At this point, I want to go on to a very different idea for shrinkage. A much simpler one, though. It's called subset selection, specifically subsets of the features. Now, some of you might have noticed way back when we did homework 1 that if you leave out some of the features in the spam competition, you sometimes get better results. Because what's happening is a lot of the features in spam don't have much predictive power, or have none, and they still increase the variance. Every feature we add increases the variance, but is only worth keeping if it reduces the bias more than it increases the variance. So leaving out useless features can be a big win for getting better generalization. Spam is a classic example where that happens. So again, keep in mind that all the features increase the variance, whether they're good features or bad features, predictive or not predictive. But only the predictive ones help reduce the bias. And sometimes too many predictive ones don't reduce the bias because they're just encoding redundant information. So you want to keep the features that will help you reduce the bias, but throw away the ones that won't. So the idea of subset selection is we're going to try to figure out a way to identify which ones we can throw away. And by throw them away, one way to operationalize that is to set their weights to 0. And if you have a lot of really poorly predictive features, then the advantage of that, obviously, is you get less overfitting, and therefore, whether or not your training error looks any different, your test errors ought to go down. That's not the only possible motivation. There's a second reason why you might want to do this, which is, remember, sometimes we use machine learning algorithms to do inference. we want to not just classify or regress, we want to actually understand what the relationships are to our features and why. And so for that purpose, we want to throw away poorly predictive features so that we know that they're poorly predictive. That's part of our scientific model that we're building. And the fewer features you have to look at to come to a conclusion, the easier it is to interpret the things learned by your learning algorithm. And one thing I want to emphasize is that subset selection is a very general method. Just like you can add new features to almost any classification or regression algorithm, you can also subtract features in almost any classification or regression algorithm. And if they're poorly predictive features, it'll be a win. Having said that, okay, now at this point, we've got this list of features. We want to identify the best subset of those features that'll give us the best test error or test accuracy. But that's generally hard because there's an exponential number of choices. And part of what makes it tricky is that there are interactions between different features, because different features can partly encode redundant information. And when true, it's actually combinatorially hard to choose the best subset of features in polynomial time. And so there's several algorithms that people use as heuristics to try to approximate a good set of features, but won't necessarily find the optimal set of features. As a counterpoint to those algorithms, let me first, though, give you an algorithm which is generally too slow to use in practice unless you have a very small number of features. But I just want to describe this algorithm as sort of the competitor, the ideal competitor that we are trying to emulate. This algorithm is called best subset selection. And the way it works is that you actually try every possible subset except the empty subset. For each subset, you train a classifier using those features. Then you choose the best classifier from all those different classifiers by validation or cross-validation as usual. The obvious problem with this algorithm is it's slow. Especially because you have to train 2 to the d different models. If d is small, like if it's 5, maybe even if it's 20, you might find it worthwhile to do this. But if d is really big, like if you're doing image classification, this is totally impossible. You're not going to finish this in your lifetime. Because it's exponential in the number of features. But again, the reason why I'm writing down this algorithm is just as something to compete with. Well, we're going to design heuristics, and we hope those heuristics will at least very approximately give us something almost as good as this would give us. And so there are two heuristics that are used a lot in practice. One of them is called forward stepwise selection. The other one is called backward stepwise selection. Some of you can probably guess just from the names alone what these do, because they're not very complicated ideas. It's basically doing the obvious thing. Forward stepwise selection, the way it works is it starts with what's called the null model. The null model is one that uses 0 features. We don't actually try to train that model. But from that point, we're going to have a loop that repeatedly adds the best feature. All right, so you have a loop that repeatedly adds the best feature, the feature that most improves your test accuracy. And you keep doing that until no feature improves your test accuracy, and then you stop. How do you know which feature is going to improve your test accuracy? Well, you have to try them all. So this algorithm is actually a doubly nested loop. The outer loop, each iteration adds one feature. The inner loop tries all the features that haven't been added yet and tests each one, trains one model for each one. All right, so the inner loop is going to try every feature that hasn't been added to the model yet and see what happens if I add just this one additional feature. And for each iteration, you have to train a model and evaluate it on the test data or the validation data. And ultimately, that means you have to train d-squared models. The number of models you have to train is quadratic in the number of features, which sounds a little slow, but it's a lot better than exponential. And by the way, sometimes you stop early. If there are only a small number of predictive features and a lot of not predictive features, then it won't actually take d-squared time, because as soon as you run out of predictive features, it stops. So that's why this might be a good choice for spam. Now, I just want to be clear that this model is not perfect. It will not always pick the best features. For example, will it find the best model with 2 features? Well, it is actually possible that neither of those two features in the best two-feature model give you the best one-feature model. So if you have a situation like that where the best model with two features, neither one of those features alone gives you the best feature model, you're not going to find the best two-feature model. That's why it's a heuristic. But it's still often very well in practice. Now, the second heuristic is very similar to the first one. It's called backward stepwise selection. And here, instead of starting with the null model, you start with the loaded model, which has all D features. And then you just keep removing features that are not predictive. Otherwise, it's basically the same as forward stepwise selection. Once again, you have a doubly nested loop. The outer loop is removing one feature at a time. The inner loop is trying each feature to see what's the best feature to throw away. The outer loop can terminate early if there's no feature that you can throw away that improves your validation data. Once your validation accuracy is not improving anymore, you stop the outer loop. You stop the whole algorithm. And hopefully it's obvious that this, in the worst case, also trains d-squared models. Now, backward stepwise selection is probably the best choice if you believe that most of your features are good, predictive, helpful features. So like the opposite of spam. For spam, forward stepwise selection is obviously going to be better because we're not going to keep more than a small fraction of the features. Any questions about any of this? Yeah. Mm-hmm. Right. Oh, well, I'm using information in a somewhat vague way, but the simplest example would be, suppose you have two features and the second feature is always 3 times the first feature for every data point. Then they're totally redundant. Whatever information is encoded by one feature is encoded by the other, and having both of them gives you absolutely no advantage. Does that make sense? Well, correlated, yeah. When features are correlated, they have some redundant, they carry some redundant information. And this gets more complicated when you have a nonlinear method where the way in which information can be represented is nonlinear. So keep that in mind too, because this isn't just for linear regression, it's for any classification or regression algorithm. Yeah. why isn't the fact that they have low predictive power captured by least squares? That's a good question. The main reason is because we're seeing that there's some noise in the data. When you have noisy data, you can almost always find some spurious correlation between the noise and the thing that you're trying to model. That's just a fact of working with data, and it's one of the reasons why so many people come to so many wrong conclusions based on data, is because they don't realize that they're fitting to the noise. There's nothing special about least squares linear regression that allows it to know that it is seeing a completely spurious correlation rather than a real one. And wherever you have noise, you're going to have spurious correlations. The last topic for today is another regularization method called lasso, which is a relatively recent invention of a guy who actually wrote, I think, one or both of your textbooks for this class. He's a co-author. And this is, I think, his most famous piece of work from 1996, so one of the most, so very recent. And this is going to tie together the last two topics. So it's a lot like ridge regression. It's just it uses the L1 penalty instead of the L2 penalty. But it also has a lot in common with subset selection, because one thing lasso does often is it sets some of the weights to 0. It figures out that features are not very strongly predictive and just gives them 0 weights. And so based on optimization, it kind of implicitly figure out which features are not very predictive. Lasso is an acronym. It's short for least absolute shrinkage and selection operator. Which I think is one of the best acronyms I've ever seen. The words actually tell you what the method does. The objective function is the same as ridge regression, except we're just changing the norm, and we're not squaring it. So here's the least squares regression part. That's not changed. Here's the penalty term, and this is going to be the L1 norm of W, W prime, instead of the L2 norm, and again, we're not squaring it. And if you've forgotten what the L1 norm is of a vector, it is the sum of the absolute values of each of the components. And once again, I think that usually I do not recommend penalizing alpha, the bias term. So I left that out. But you can if you want to. All right, so in ridge regression, remember that the isosurfaces of the penalty term are spheres, or it's common in higher dimensions to call the higher dimensional analogs of spheres hyperspheres. Okay, but what are the isosurfaces of the L1 norm? Well, they're a geometric object called cross polytopes. What is that? Well, the unit cross polytope is the convex hull of the unit coordinate vectors including both the positive pointing ones and the negative pointing ones. Let me draw that so you can see what it means. So here, consider the two-dimensional case. Suppose we have a two-dimensional feature space, not counting the bias term. Those are the positive unit coordinate vectors. Here's the x direction, here's the y direction. These are both vectors of length 1 in those two directions. We're also going to throw in the negative ones. So one more in this direction, one more unit vector in this direction. And now we just take the convex hull of those 4 vectors, which means basically I wrap a piece of string around them. And the shape I get is a diamond shape. And in 2 dimensions, that's what the isocontours look like. They look like diamonds. What if we go to 3 dimensions? Well, we'll still have the x-axis, we'll still have the y-axis, but now we'll also have a z-axis. So that's 6 vectors in 3 dimensions. Now what I'm going to do is take the convex hull of those, and that means that I'm going to get a triangular face here, a triangular face here, a triangular face here, and a triangular face here. And then there will be 4 more triangular faces on the back side, behind you, hidden. So this is an octahedron. It has a total of 8 sides, each triangular. In general, if you have d features, you're going to get a polytope with 2 to the power of d sides, 2 to the d facets. These are the unit cross polytopes. You can get bigger cross polytopes or smaller ones just by scaling these, and that gives you the rest of the isocontours of WL1 norm. So now let's revisit our intuition for ridge regression, only this time we're going to use the L1 norm instead of the L2 norm. What happens? Well, on the right is ridge regression. Just to remind you what I already showed you. On the left is lasso. And so now we have these diamond-shaped isocontours instead of circular isocontours. And the solutions, depending on the value of lambda that we get, are these points here. So again, those are the possible solutions for different lambdas. And you can actually draw a curve, except now it's not a curvy curve, now it's just 2 straight lines that show you all the different possible values you might get for different values of lambda. Now the thing that's interesting here is that quite often the optimum will be right at the tip, one of the 4 tips of the diamond. Now, not always, sometimes that doesn't happen, but when it does happen, well, that's particularly interesting because that sets one of the weights to 0. And in higher dimensions, you could get any number of weights set to 0. Well, there's always one non-zero weight, but almost all the weights could be set to 0. None of the weights could be set to 0, anything in between, depending on what is justified by the data. But this kind of regularization does tend to take small weights and set them to 0. Now, there is an interesting illustration in one of your textbooks that shows what happens to the weights in a simple ridge regression problem. I think this one has 10 10 variables. So there are 10 variables here. And the x-axis here is we're increasing the regularization parameter lambda, more regularization. And what's plotted here are how each of those 10 variables change as we crank lambda up. What you'll notice is that there's a bunch of small variables that get extinguished first, and then there's some bigger ones that get extinguished later. And so the little ones probably don't have much predictive power, even if they seem to have a tiny bit. The big ones probably do have predictive power, and we should keep them. The way that statisticians used to lasso is that they would eyeball this chart and they would pick a good value of lambda that seems to preserve useful data while leaving out the wrong data. They just use validation. Validation is the answer to everything. Just validate and figure out which value of lambda gives you the lowest validation error, and we're happy. Any final questions about this? All right, thanks so much. Well, come up and ask me.